Well, thank you. I'd like to thank the organizers for inviting me to the workshop. Presumably, they invited me as one of the older scientists here. Something I've been involved in climate change science for, that's probably yours, for 40 years on climate change or something, that some of this will come up. So I've been asked to talk about what might be said to some of the early science. It seems appropriate to say it's equivalent this morning to reading from the Old Testament, so to speak, to summarize and offer commentary on the prophecies of early times and stuff. And so I've actually sort of retitled my slide that way. I can see or imagine that the headlines, I would say, but you'd all say tweets, will now say that climate change believers are holding a revivalist meeting on 8 a.m. on a Sunday morning at a remote place in Colorado to figure out how to better tell their old story. And so I'm going to sort of do this. It does raise a question, perhaps, in thinking about how successful religion has been, that all the old religious texts have survived without graphics. It's all been based on the word. And so, like it turns out, the early climate scientists and prophecies are a lot like that. So there's going to be a lot of words on these graphics, and on these slides, and we can talk about that. All right, so just a few definitions. I'm going to sort of be a personal or incomplete retrospective about it. Biased, my stuff I started becoming involved in climate change in the 1960s, way back in the mid-60s, doing climate change things. So I'll be drawing mostly on pre-IPCC, what is that, PI or something like that. From the sort of through into the up to the sort of mid-'80s. I learned the other day that actually that's the time that Michael Mann was graduating from high school. So that's the reference period we'll be using here. And it's going to be from a physical scientist point of view. You're going to hear from Spencer talking about policy aspects. But let me just say a few things. It's kind of intriguing how early on a number of the key ideas arose. They had a lot of the physics ideas very early. It's interesting on some of the mistakes, and I'll sort of point out a few of those. And it's interesting how some of the early criticisms that came up, and some of them, many of them, actually sort of still persist. We haven't been beating them down. Okay, and so now let us learn from the lessons of the early prophets, I guess, or something like that. So in the 19th century, the idea of IR absorption and greenhouse gases and how the atmosphere was structured came up in the mid-19th century. A lot of people have heard of Arrhenius in 1896, who made sort of the first calculation of how changing CO2 would affect the climate. They were interested at the time about what was the cause of ice ages, and so it was actually related to cooling rather than warming. He did also do warming, but the impetus at the time was about cooling. And it's really interesting. That early study so long ago treated water vapor feedback, the idea that as temperature went up, water vapor would go up. And they actually had the notion of snow and ice albedo feedbacks in there. So some of these real ideas came up really early in what happened. There were early papers about what was going to happen to the carbon cycle. That is, they'd realized that humans were adding CO2 to the atmosphere. If you burn coal, it isn't getting reestablished instantly. It's sort of going into the atmosphere, and that would cause a change in concentration. They sort of didn't project the increase in use that occurred, but they did have a notion that it was going on very strongly. Now, there were two key criticisms of that early work, or I'm going to summarize it in terms of two key criticisms. The first one that was that looking from the surface, if you looked at the CO2 bands, they looked saturated. And so how could adding CO2 to the atmosphere warm it if you essentially had saturated bands? And that took a while to resolve. So the notion was CO2 wouldn't have much effect. And the other was that the ocean has lots of CO2 in it, and so the atmosphere doesn't have all that much. And so how could you raise the the atmospheric concentration, wouldn't it all go into the ocean and get apportioned into the ocean? So those are sort of two criticisms, and they were rather long-lasting. We'll come back to it. So a lot happened sort of over the next 50 years. Richardson did the first attempt to actually do a model by hand calculating the advance of the weather and during World War I, sitting there as an ambulance driver when he was idle. Guy Callender actually was sort of one of the strongest proponents of the CO2 kind of thing over this period. And by the way, anybody can have these slides if you want, so don't take too many notes here. So he had a sense that, well, he thought it was important. He had a sense that he had measured an increase in the CO2 concentration, even though the measurements were rather uncertain, and they were probably done in areas that were being affected by local emissions. He sort of didn't think the oceans could absorb all the CO2. He sort of had insights about pressure broadening, about the window effect in the IR effect, that glaciers were changing. And he sort of got a CO2 sensitivity, and his estimation was sort of about 2 degrees. But he described the physics actually amazingly well. There's a very good book by Jim Fleming about this. The next one I wanted to put up, there were other things, was Harry Wexler in 1953 in a book. It was a book about what's causing the ice ages. At the time, there were a lot of hypotheses about it. Milankovitch was one hypothesis, but it was hard to understand how small changes could have a big effect. But there was a whole very interesting book about it, climatic change. But Harry Wexler was a very prominent meteorologist, later became head of the prediction center and stuff. But if you look at he was the only one, I think, in the book that talked about the CO2 effect, and he talked about how the radiation balance of the Earth could have an effect. But one of his criticisms was he didn't understand how Callender's hypothesis about the fact, realizing that that the temperature decreases with height would be an important kind of thing, and how the greenhouse effect worked, how that could really work when you had an inversion, because there were inversions over land and ocean some fair fraction of nights and of the time. And so here was actually an interesting criticism even in the mid-20th century. That was also a time when the start of numerical weather prediction models was occurring on early computers and things. Most of those models, when they were doing them, focused on dynamics. The early weather models had no radiation. They just started with dynamics and ran it. And if you ran it for a while, what's that going to do? Well, the Earth's going to come to equilibrium. Everywhere will be the same, right? I mean, there was no gradation of solar and long wave. That was just something they weren't doing at the time. So that got added later, but it was really interesting. And I raise this because there's an important dividing point that occurred, and I think we're having to bring this back together at the time, and that is climate change studies separated from numerical weather prediction studies, at least in this country. And it became different groups, different people to a large extent. There were some good reasons for it because of how you have to do statistics and running climate models, treating lots of other processes than weather prediction. But it did separate us from dealing with issues like extreme weather. When you start taking 30-year averages of things and talking about the climate, the fact that you have a big anomaly in the US on the East Coast and an opposite anomaly on the West Coast sort of lets people think that it's variability instead of change. So that was something that didn't happen. I think we need to reflect on that. I want to raise another sort of iconic paper, and that's the one that's quoted a lot, Ravel and Zeus, who are credited with addressing this issue of the carbon cycle and the ocean uptake and the delay. And they basically had a statement that's quoted a lot. Human beings are now carrying out a large-scale geophysical experiment of a kind that could not have happened in the past. And that's what that paper is remembered for. What's sort of omitted is their estimate of the lifetime of CO2 in the atmosphere. They did an estimate. There was a lot of discussion going on at the time about what would happen, and there were people doing radionuclide studies and other things about uptake in shells and a bunch of other things. But Ravel and Zeus did a paper, and they basically, with their isotopic studies, came out with a suggestion that the lifetime of a CO2 molecule in the air is about 10 years. Now, that actually turns out to be correct for a particular molecule. But if you want, it does not reflect what happens on the persistence of the perturbation in the atmosphere. Now, they talk some about that and how slow the removal rate is, CO2 is from the ocean, but they gave this notion of a 10-year, a short lifetime, some credence here. And one of the questions that sort of came up as I was going through is whether the confusion about this, about having a short lifetime, rather than this notion of a long time building up, is one of the reasons that there was this controversy about, is the world going to warm or cool? There was Reed Bryson and a number of others who were saying we're increasing the particulate loading of the atmosphere so much that it's going to lead to cooling. Sulfate and other things were going to lead to cooling. Or we might have CO2, which builds up over time and lead to warming. But if you have a lifetime of 10 years, that doesn't come across. And so there is confusion about using lifetime and residence time and a bunch of other things. So that's part of the confusion we've perhaps had in our field. So then a lot more things were happening. There started to be measurements during the International Geophysical Year. CO2 concentration was rising. Keeling did the Mauna Loa curve and everything. It was recognized at that time that the CO2 was a rapid uptake into the upper ocean, but not to the deep ocean. And so there were estimates of what the time was. And there you see then that the CO2 time of the perturbation would be centuries with components that would go out even further than that. So there was sort of insight that came from that. There's another iconic paper, Manabe and Weatherald in '67, who addressed this issue of how the greenhouse effect worked in a convincing way with a lot of modeling with a one-dimensional radiative convective model, and showed a climate sensitivity of about 3. Although I will point out that our statements that CO2 greenhouse causes the atmosphere to warm are objected to strenuously by a particular critic from Australia, who points out, actually correctly about our explanation, that if you add CO2 to the atmosphere, it causes the atmosphere to lose energy. That what's happening, lose more energy, that what's really happening is convection is adding more energy to the atmosphere. And so what CO2 has caused the surface atmosphere system to warm, but it doesn't cause the atmosphere to warm on its own. So, and now this person is a little strange because they basically say because IPCC doesn't understand that, therefore you have to question everything of IPCC. But aside from that, you can have interesting discussions with them. I also want to go on to say that once people had an understanding the greenhouse effect was real, and that we were affecting the climate, that we'd solved the greenhouse effect and this carbon rise effect and everything, there was a report written to the President of the United States and the Congress in 1965 from the President's Science Advisory Council. So the first official report to the US government on this issue is 1965. And so I'm going to go through these findings because they're actually kind of interesting. It had a wonderful committee, if you'll look at it, Revell and Wally Broker, Harmon Craig, who was an oceanographer, chemical oceanographer, David Keeling, Joe Smagorinsky, GFDL. So they had some findings on the carbon cycle, that that human production is a lot more than the weathering can take up, that within a few short centuries we're returning a lot of carbon to the atmosphere that's been accumulated over 1 billion years and half a billion years. That not all will remain in the atmosphere, but there will be a significant effect on things. That their fraction was actually, that the airborne fraction was about 1/2. That's still within a few percent of the present estimate. And that the ocean uptake was about 15%. That's a little low compared to what it is today, so they were assuming there was a lot in the biosphere that was going on. So there's some key projections on future composition, that it's going to go up. They sort of talked about burning all of the recoverable fossil fuels in the next 150 years, so by, 2115 or something. The CO2 would increase nearly 170% the concentration, which if you calculate it's about 750. And so they had about 350 to 450 ppm by 2000, so they were sort of bounding the problem pretty well. They did some learning from about past climates, about where things had come from. They had this issue about what had happened between 1940 and 1960, where you got warm and then there started to be some cooling that they had to deal with. And they suggested that there were other factors involved that were masking it and stuff, that the CO2 increase they'd seen couldn't have caused the warming, couldn't be the whole responsible fraction or something like that. So we can go over. Now, there were some projections of climate change. They actually focused and said a useful projection would be what would happen with a 25% increase in CO2. They sort of had the stratosphere would cool, and they had that there would be, various kinds of warming that would go on. They made a statement here that I'm going to come back to about modeling that will be able to make useful predictions. So that meant regional predictions with a 25% increase in CO2 in 2 to 3 years. Can we do that now? Yeah, okay. All right, but I'll come to that in just a moment. But they had, deleterious effects on human beings. They had a number of the kinds of impacts. Here are some of the melting of Antarctic ice cap, rise of sea level, warming of seawater, increased acidity of fresh water. So they had acidification, but they had it of fresh water instead of salt water. Kind of intriguing. Increase in photosynthesis. Okay, so let's look at this statement about modeling. It was actually quite amazing. It's probably the one thing you'd call a mistake in their report. This was a statement that was made before the notion of what Lorenz had discovered about nonlinear dynamics and chaos had really penetrated into the community. The idea was, I can construct these great models. They're nice deterministic things. I'll be able to see the future that way. And we learned soon after about the problem with that. Okay, so I'll just say there was a number of other things going on. Mikhail Bedico, William Sellers in his book, Study of Man's Impact on Climate, all were sort of saying and had the science pretty well right. In 1975, I was advising DOE, the start of the Atomic Energy Commission became ERDA, and they took on the acid rain program. I said they should take on the CO2 problem. And they sent my letter out to a bunch of people who all said, oh, yes, you should, and advocated a research program. So there was agreement on it, even by Reggie Newell, who a few years later was saying the opposite. There was a WMO workshop, so it was an international issue in 1976 that basically made quite good statements. 1 degree by 2000, 3 degrees by 2050. There was stuff in the press about crazy weather going on in the 1970s. Time magazine talking about the climate unpredictable. New York Times having a very balanced statement saying the effects of a century of fossil fuel burning could take a millennium to dissipate, and you should go with that. And I want to get through these last few things, so I'll hurry. There was the Jewel Charney sort of led NRC study that basically came out with 3 plus or minus 1.5 degrees after looking at everything and trying to shoot everything down. There were improvements to GCMs of a lot of kinds that went on in the 70s and early 80s. The interesting thing about it is it didn't change the climate sensitivity much at all. I mean, even if you went to annual to seasonal, specified to interactive clouds, all these things stayed the same. But there were many questions, and there still are many other ones that were constant at the time. There were huge arguments about the land carbon term between Wally Broecker and George Woodwell, additional gases, sulfate aerosols, analog estimates of climate change, paleoclimate, and other things. There were a number of major workshops that DOE convened, one on impacts. It doesn't get much attention by now. It's run by AAAS, has 20 supporting documents, a workshop on environmental and societal consequences. There's a major NRC report in 1983. And then the Department of Energy had some state-of-the-art assessments, I should say state-of-the-art assessments there, that were done in 1985, and I just want to sort of quickly put up some others. There were 3 of them that had to do a lot with climate, detecting climatic effects of increasing carbon dioxide. This is where Phil Jones and some of these others addressed the issues of urban warming and things that came up in ClimateGate. They all go back to this actual document. DOE was supporting that kind of research. Projecting into the future about what models are, what sensitivities are, and a whole host of things. And an NRC report on glaciers and ice sheets and sea level and other things. And they had things surprisingly good shape. Finally, the conference that I want to end with is the VLOC conference, which was, given all of this, what should we tell policymakers? And so UNEP and WMO and ICSU convened a conference of the two basically saying things you would say today. Many important economic and social decisions are being made, assuming on long-term projects based on the assumption past climatic data is right. Climate and sea level are closely tied to other issues. Some warming is inevitable, but policies can make a difference. We had coverage on the front page of USA Today. One of the things we often say we're lacking is a spokesperson. There was a spokesperson back then who got a lot of publicity. Carl Sagan. Let me show you what he did. Sometimes you have to be cautious about spokespersons. He really talked about, if you read the caption, it's right. If you melt all of Antarctica, that's what happens or something, but that was kind of a far-fetched thing. So just a few lessons for discussion. Many things were identified early on. I think separating from numerical weather prediction was important. All this focus on research and getting to being right current got us away from continuing to focus on fundamental issues, which make this issue of concern all the way. And so the media doesn't educate, it stays at the cutting edge, and we really need to get back, I think, to doing fundamentals and things. So finally, may the revealed, or as former vice president would say, revealed, words of the early prophets be revered and their few errors forgiven. Thank you.